Hello friend. Now last time we have seen the definition of the convergent sequence. Now see what is the definition of the convergent sequence. If suppose Sn, it is the infinite sequence of real numbers suppose, then this sequence Sn converges to the limit L means that for epsilon greater than 0 there exists a natural number n such that modulus of Sn minus L, this is less than epsilon for all n greater than or equal to capital N. So see, this is the definition of the convergent sequence. What is the definition? Sequence Sn, this is converges to the limit L means that for every epsilon greater than 0, we have to find out this natural number n such that after this natural number, small n it is greater than or equal to capital N means after this natural number, all the term of the sequences, it is lies between epsilon neighborhood of this limit. What is the meaning of this convergent sequence? If the sequence Sn, if it is converges to the limit L, means that for epsilon greater than 0, there exists a natural number such that after this natural number, all the term of the sequence, it is lies in between epsilon neighborhood of this limit. Now see, this is the theorem. If suppose the sequence, if it is a convergent sequence, then show that this convergent sequence, it converges to unique limit. See, what is this theorem? We want to show that limit of the convergent sequence show that it is always the unique limit. Now see what is given. In this theorem we are given the convergent sequence. So first of all, take Sn as a convergent sequence and show that, we want to show that this convergent sequence Sn, it converges to unique limit. So let us write down the proof of this theorem. So first of all, we take this convergent sequence and show that this sequence, it converges to unique limit. Write down the proof. Now see, we want to show that this sequence Sn converges to unique point. Unique point means just it is a single point. We want to show that this sequence Sn, it converges to unique point. Now for this theorem, we use the method of contradiction. Now see what is the contradiction method. We want to show that this sequence Sn converges to unique point. So let us assume the contradiction that suppose that this sequence Sn converges to two different points. Suppose let us take L and N. So write down, suppose that this sequence Sn converges to two different limit, say capital L and capital N. So see, this is our starting. First of all, we have to take some convergent sequence. So let us take suppose Sn as a convergent sequence. Now we want to show that this Xn converges to unique point. Now we are using the method of contradiction. So what is the contradictory statement? Okay, suppose that the sequence Sn converges to two different limits, say L and M. Now see, L and M, these are the different points. So right here, okay, since L, this is different from M, so obviously this L minus M, this is a non-zero number. Because these are the different points, L and M, these are two different limits. So if we take suppose the subtraction of L and M, so obviously it is a non-zero number. So modulus of L minus M, if we take the absolute value of L and M or absolute value of L minus M, so obviously this is again a positive number or this is a non-zero number. Let us take this as a positive number. So modulus of L minus M, it is greater than 0, or if we suppose multiply by 1/2, then 1/2 of modulus L minus M, this is again the positive number. So see, we have taken Sn as a convergent sequence and suppose that the sequence Sn converges to two different limits L and M. So as L and M, these are the different points, so we can say that L, it is different from M. So if you take the subtraction of L and M, obviously it is a non-zero. If you take the absolute value, then it will be positive value, and if you multiply by 1/2, then 1/2 of L minus M, this is again greater than 0. Now see, we want to show that this sequence Sn converges to unique limit. So what is given? We are given that this sequence Sn, we have taken this sequence Sn converges to two different limits L and N. So we use this concept that sequence Sn converges to L and sequence Sn converges to N. Now see, what is the definition of the convergent sequence? If suppose Sn, it is the convergent sequence, and if suppose it is converges to L, then what is the definition? We have to choose epsilon greater than 0 and we have to find out the integer n. Having the condition or satisfying the condition that modulus of Sn minus L, this is less than epsilon for all n greater than or equal to capital N. So first of all, we choose this epsilon which has a positive number. Now this is the positive number. So let us choose epsilon equal to 1/2 modulus of L minus M. So right here, we choose epsilon is equal to 1/2 modulus of L minus M. Now let us use this concept. We have taken this sequence Sn, it converges to two different limits, it is L and N. So first of all, we use the concept that sequence Sn converges to L, use the definition of the convergent sequence, and then use this definition that sequence Sn converges to different limit, that is N. So write down, since the sequence Sn converges to limit L, that is, this sequence Sn converges to limit L. So what is the definition of the convergent sequence? Just now we have seen the definition of the convergent sequence. What is the definition? For epsilon greater than 0, there exists a natural number, n1 such that, what is the condition? That modulus of Sn minus L, it is less than epsilon, and this condition it is true for all n greater than or equal to, suppose, capital N1. So instead of this, we are using this natural number n1, so this is suppose the equation number 1. So see, we are using this concept that sequence Sn converges to two different limits. So first of all, use the first concept कि sequence Sn converges to the limit L. So this is a definition. Now use now the second concept कि sequence Sn converges to second limit, it is M. So right here also sequence Sn converges to limit M. So what is the definition? Use same definition. Therefore for epsilon greater than 0 there exists a natural number, let us take suppose n2, such that what is the condition? The modulus of Sn minus m, this is less than epsilon, and this condition it is true for all n greater than or equal to n2. This is suppose equation number 2. So see, just we are using the definition of the convergent sequence. What we assume? We assume the sequence Sn converges to two different limit L and M. So use the first concept, the sequence Sn converges to first limit, it is L. So this is the definition, which is our equation number 1. Secondly, assume that the sequence Sn converges to second limit, which is M. So this is the definition of the convergent sequence. So this is the first equation and this is our second equation. Now see, this first equation, it is valid for all n greater than or equal to this natural number n1. And this second equation, it is valid for all the natural number which is n2. First condition, it is true for all n which is greater or equal to n1. This second equation, it is valid for all n which is greater than or equal to this natural number n2. Now if it is suppose the maximum between n1 and n2, see the equation 1 it is valid for n1, equation 2 it is valid for n2. Now if you take the maximum between n1 and n2, then the same condition it is valid for the maximum number. So let us use the maximum number. So right here let capital N, this is the maximum between n1 and n2. So we can write this equation 1 and 2 as, so right here, therefore equation 1 and 2 becomes, so what is our equation number 1? This absolute value Sn minus L, this is less than epsilon, and this condition it is valid for all n greater than or equal to this maximum number. So instead of this n1, we are using the maximum. We are taken this maximum as capital N, so use this notation capital N. Also we can write this second equation. Also, what is the second equation? Modulus of Sn minus m, this is less than epsilon, and this equation it is valid for all n greater than or equal to capital N. Now we want to show that this sequence Sn converges to unique limit. Limit of the convergent sequence, it is always unique. So for that we consider this term. So right here consider modulus of L minus M. So simplify this absolute value. So this is modulus L. Now subtract Sn and add Sn. So there is no change, minus M as it is. Just consider this modulus of L minus M. So what is this step? Just subtract Sn and add Sn. So there is no change. Now this is the formula. Modulus of x plus y, this can be written as less than or equal to mod x plus mod y. If we use as the first term, if we use this as the first term and use this as the second term, so this is exactly the same formula, which is modulus of x plus y. So what is this formula? This is less than or equal to modulus of first term L minus Sn plus modulus of second term Sn minus M. Now see, what is this equation? L minus Sn, modulus of L minus Sn, this is same as modulus of Sn minus L. So from this equation we can put this value. This is less than epsilon. if you use, suppose this is the equation number 3 and this is the equation number 4. So from equation 3 we can put this value. From equation 4 we can use this value, okay, modulus of Sn minus m, it is less than epsilon. So epsilon plus epsilon, this is 2 epsilon. Now what is this left hand side? Left hand side is modulus of L minus n. Now we have taken this epsilon equal to 1/2 modulus of L minus n. So just put the value of modulus of L minus n. What is this value? Modulus of L minus m, just cross multiply by 2. So it will be 2 epsilon. So what is this value? 2 epsilon. This is less than 2 epsilon. So this is the incorrect. So this is our contradiction. So this is contradiction means obviously what we have assumed, it was the wrong assumption. What is our assumption? The sequence Sn converges to two different limit L and m. That is the wrong assumption. So what is the correct assumption? The sequence Sn converges to unique limit. So right here, which is contradiction, that means our assumption is wrong. Which assumption? Sequence Sn converges to two different limit. That assumption, it is wrong. So what is the correct assumption? Sequence Sn converges to unique limit. So right here, therefore, the sequence Sn converges to unique limit. So this is the complete proof of this theorem. So what is our theorem? To show that limit of the convergent sequence, if it exists, then show that it is the unique limit. Thank you for watching.